So it's a pleasure to be able to talk with you today. So I got my PhD in theoretical physics from the University of California in Berkeley in 1966, a long time ago. Before that, I was a student at Harvard as an undergraduate. And after I graduated from Berkeley, I was 6 years on the faculty at Princeton University. And after that, I moved to the California Institute of Technology. So I've been here in Pasadena, California for over 50 years. And I retired as a faculty member 9 years ago. But I still try to keep a little bit involved with what's going on, even though I'm no longer teaching or advising students. So turning to the subjects that have interested me, when I was an undergraduate, I was a major in mathematics. I thought I was pretty good at that, and I enjoyed learning mathematics. But at some point when I was considering going to graduate school, I decided to switch to theoretical physics. And there were a couple of reasons for doing that. One was that mathematics, while it's enjoyable and fun, seems rather distantly connected to the real world. And in theoretical physics, one uses lots of mathematical tools, but with a specific purpose in mind, which is to describe the universe in which we reside. So that seemed to me a good motivation to switch to physics, which is what I did when I went to graduate school. So when I got to Berkeley, after a year, the first year taking courses, after that, I became an advisee of Professor Jeffrey Chu. Chu was pretty much the founder of an approach to theoretical physics in that era that was called S-matrix theory. And the problem is as follows, that there are several different kinds of forces in nature that act on various particles. And one of them is the electromagnetic force. And that was, by that era, that was already very well understood. The revolutions in relativity and quantum theory that had taken place earlier in the 20th century had led to a very successful theory of the electromagnetic force called quantum electrodynamics, QED for short. But we knew that there were other forces, and one of them is the strong nuclear force. So the story there is that if you think about the nucleus of an atom, which contains a bunch of protons and neutrons, there needs to be a force that holds those particles together. Because if you only consider the electromagnetic force, the protons are repelling each other. They all have the same electrical charge. So you need a stronger force to hold it all together. And that force is called the strong nuclear force. And at that time, there wasn't a successful theory of what that is. And so that was the goal of the research that Jeffrey Chu was engaged in, and I, as one of his students, also became engaged in. And this approach to, he had a specific approach called S-matrix theory. And there was another approach that many people around the world were also pursuing at the same time, which loosely could just be called quantum field theory. And that's the approach that had been so successful in this case of quantum electrodynamics, QED, electromagnetic theory. So the argument against using a quantum field theory at that time was that it was known that the strong force, as the name suggests, is strong. And that means that if you identify an interaction strength and consider describing effects by some sort of expansion in that strength of interaction, that kind of an expansion would not converge well because the expansion parameter is just too large. And so the S-matrix theory approach tried to circumvent that problem by just cleverly finding the final answer right off the bat without just doing it as an expansion in some small parameter. So this S matrix theory was based on various principles that were called bootstrap principle and Reget-Pol theory, all sorts of technical stuff I won't attempt to explain. But in 1968, sort of midway through my, excuse me, so in 66, I moved to Princeton. And in 1968, there was kind of a breakthrough in this S matrix theory approach due to an Italian physicist, Gabriele Veneziano. And what Veneziano did was to write down a formula involving well-known expressions, the mathematical expressions that people understood, that was sort of a guess at the final answer for a certain type of process. And while that was clearly not a realistic theory of anything, that formula had many of the properties that were trying to be realized in the S matrix theory approach. And so people got very excited about Veneziano's formula and developed various generalizations of it to describe other kinds of processes and more particles and so on and so forth. And I got involved in that starting around 1970 and in Princeton. And during that period, people actually developed a kind of theory that incorporated Veneziano's formula in a more consistent framework involving more kinds of particles and so on and so forth. But it's still not a realistic theory, but at least it was a mathematically sensible one. And so we wanted a more realistic theory. And at that time, I was collaborating with a French fellow, André Neveu, who was a visiting fellow in Princeton. And together, we found a second theory, second theory that had the same virtues as the Veneziano theory, but it was somewhat more realistic. It wasn't completely realistic, but it was more realistic. So this was in 1971, and that caused a lot of interest and led to a couple of important developments in the subject. One was the discovery of a new kind of symmetry called supersymmetry, which, even though that we hadn't set out to discover it, it turned out to be a feature of the theory that we had introduced. And it has been a major theme in particle theory ever since, even though there is as yet no experimental evidence for it. So this led to a theory with supersymmetry. To explain just roughly what supersymmetry is, there are two kinds of particles called bosons and fermions, and all the previously known symmetries would relate different kinds of bosons to other kinds of bosons, and similarly would relate fermions to fermions. But supersymmetry was the first kind of symmetry, and the only kind of symmetry that relates bosons to fermions. So that looked promising for tying more things together, which is always what we're trying to do in this business. So that's where things stood for a while. And then in 1973, what I should say before 73, is that at some point people realized that these formulas we were writing down could actually be interpreted as describing the behavior of one-dimensional objects, lines, loops, and so these were, people started calling them strings. So the subject then became called string theory. So we had the formulas for some time before we had that interpretation. But in any case, the subject is now referred to as string theory. So in 1973, a new theory of the strong nuclear force called QCD, or short for quantum chromodynamics, was introduced by a bunch of people, one of whom was David Gross, who was a classmate of mine in Berkeley. I had also studied with Chu at the same time. And this quantum chromodynamics very clearly became clear that it was the correct theory of the strong nuclear force. And as a consequence of that, people stopped working on string theory. Here was the answer, and it wasn't string theory. So, so there had been several hundred people, maybe even 1,000 people working on string theory up until 1974 or so, but suddenly it was down to just a handful of people. And I continued working on it together with another French collaborator named Joël Scherk. And in 1974, Joël Scherk and I realized that even though we were not finding a successful theory of the strong force, that our theory actually contained gravity. We had not set out to define a theory of gravity. It wasn't what we wanted, but there it was. And this got us very excited because we knew there was a problem, and this could potentially solve that problem. So the problem is that the two big revolutions in physics in the 20th century were relativity and quantum theory. And relativity has two aspects to it. One aspect, I mean, both were developed by Einstein, but the one that was relevant here was the theory of gravity, which improves on the theory that Newton had put forward several hundred years earlier. And so in the general theory of relativity, gravity is associated with a certain kind of particle called graviton, in much the same way that electromagnetism is related to a particle called a photon. And we were finding that our string theory formulas contained a graviton, and furthermore, that we were able to interpret these theories in a way that was consistent with quantum theory. And so we were excited that we had a way to unify the problem of quantum theory and gravitation. So a completely different problem that got us into this business in the first place. So now we were looking for a theory of quantum gravity, which at the same time would describe all the other forces, because it has all those kinds of features. And so that was in 1974. So that was 50 years ago. And that's what I've been thinking about ever since. And the story is kind of funny because for the first 10 years, until 1984, almost no one else in the world, just a handful of people, were interested in this. And in 1984, there were some dramatic developments, and suddenly it became a major enterprise, which it's been for the last 40 years. So maybe I should stop here before I tell you anything about what happened in 84 and beyond. So I will repeat and maybe rephrase some of the things I said earlier. So as I described, these what's now called string theory arose just as a bunch of mathematical formulas that were supposed to describe the strong nuclear force. And after being developed for a length of time, people realized that in fact these formulas were describing one-dimensional extended objects. So the history is not that people set out to describe one-dimensional objects. They didn't, but that's what they did, what they achieved anyway. And that was that is the accepted interpretation of these formulas, which makes a lot of sense. And it's built into the structure of how we study it. And then on the issue of bringing in gravity, so I should first, before talking about gravity, I should point out that we already understood for quite a while that string theory could be treated as a quantum theory in much the way that theories of particles are treated as quantum theories. So the same types of tools that are used for making quantum theories of point particles could also be made for making quantum theories of these one-dimensional objects called strings. So we knew how to do the quantum theory, and we could see that it had good mathematical properties with various desirable mathematical features. And lo and behold, there was a graviton in the spectrum of particles. So you look at the different oscillation modes of the strings, and those different modes of oscillations correspond to different kinds of particles. And for a string that has topology of a loop, so it's what we call the closed string. So in the case of a closed string, the lowest excitation of that closed string, in fact, exactly has the properties desired for a graviton. And it's within the framework of what appears to be a consistent quantum theory. So even though there have been many, many other proposals for how to combine quantum theory and general relativity, Einstein's gravity theory, in my view at least, this is the only one that's had any success. I should say that there are, even to the present time, people pursuing alternative approaches to quantum gravity, but they haven't received nearly the amount of attention or success, in my view, that the string theory approach has. Okay. So I mentioned that that 84 was when a lot of people got interested in this subject, but maybe I should first say a little bit about what happened there before I address what happened in the mid 90s, 10 years later, which is what you are alluding to in your question. So one of the important features of one of the nuclear forces, called the weak nuclear force, is that it breaks the symmetry between left-handedness and right-handedness. So the fundamental physics is what is, the technical term is parity violating. And that simply means it's not the same under mirror reflection. If you took a movie of particle physics and played it back side reverse, you could tell that it violates the fundamental formulas. So that's what it means to have a parity violating theory. And parity violating theories often lead to inconsistencies with quantum theory. And because there are quantum effects called anomalies, which break the consistency of the theory. And for successful theories, these anomalies all cancel against one another, and it becomes consistent as a quantum theory. So there's a standard model of elementary particles, which contains everything except gravity. And that is a beautiful theory, highly successful, and does have parity violation. And all of these anomalies miraculously cancel. And so, which is a great confirmation for theory, at least at the mathematical level. Now, so the question arose whether string theory could give a consistent theory with parity violation. So we need parity violation because it's a fact of nature. And on the other hand, it threatens to lead to inconsistencies with quantum theory. So it was there was an important paper by Edward Witten and Alvarez Gomez in 1983, 1 year before our work, which gave formulas for all the different contributions to anomalies in different kinds of particles, and in different kinds of particles and in various dimensions of space and time. One of the things I haven't mentioned so far is that the consistency of these string theories required additional dimensions of space. And so the original Veneziano theory requires 22 additional dimensions of space, and the theory that Neveu and I pioneered, following work by Pierre Ramon, requires 6 additional dimensions of space. So it's altogether a 10-dimensional space-time theory, 1 time 9 space. So for 10 dimensions. So only in 1984 did Michael Green and I have the mathematical tools to check whether the anomalies do cancel in the parity violating string theories. And we found that one of the theories we were looking at, which we called the type 1 superstring, before you considered anomalies, was consistent for an infinite different number of symmetry types. But we discovered that the anomaly only cancels give a consistent quantum theory for one of those infinite number of possibilities, which was some mathematical group called SO32. And the second thing we discovered was we were able to test different symmetries without having a theory. So we discovered that there was another possible symmetry called E8 times E8. And the second symmetry would also enable the anomalies to be canceled, but we didn't know a string theory that had that symmetry. So that was a bit of a mystery. And a few months later, a group in Princeton constructed the string theory that has the E8 times E8 symmetry. And that theory, which they called the heterotic string theory, is currently the best candidate for giving realistic physics. There are other approaches that might work as well, but that's the one that seems to me at least to be the most promising. And that theory has features that you alluded to in your question that were understood 10 years later in the mid-90s. So the period around the mid-80s is referred to as the first superstring revolution, and the period around the mid-90s is referred to as the second superstring revolution. And we haven't had any revolutions since then, although there have been some interesting developments. One of the things that was understood about this E8 times E8 heterotic string in I think it was 1996, by Edward Witten and Petr Hržava, who's currently a professor in Berkeley. Edward Witten is a professor at the Institute for Advanced Study in Princeton. He's already retired too, actually, but he continues working. He's the most brilliant physicist of the century. There's no question about that. What Hržava and Witten discovered in the mid-90s, in 96, is that this E8 times E8 theory actually has one more dimension of space than we had realized up to that point. The reason is we studied the theory by expanding the strength of the interaction. So there's a number we call it G, but it doesn't matter what you call it. Anyway, so you have a leading approximation, and then the next approximation is G times something, and the next approximation is G squared times something. And if G is sufficiently small, that makes sense, and a couple of terms will give you good answers. But what it turned out, what they were able to demonstrate, is that in the case of this E8 times E8 theory, and also in one other theory, which is less interesting for giving realistic physics, is that when G gets large, another dimension of space opens up. And so in the case of the E8 times E8 theory, there's an 11th dimension whose size is given by this interaction strength G times some length scale, the fundamental length scale of the theory. So it's only when you set G equal to 0 that you don't see that dimension. But when you take it finite, it's there. And so the correct interpretation, taking this into account for this E8 times E8 theory, is that it's hard to visualize these higher dimensions. So let's pretend that space-time just have two dimensions. We can think about it as a flat surface. So, and then we want another dimension which has some finite length. So we think of a finite slab with two infinite surfaces, and then a little distance between and across the middle. So that distance across the middle is this new dimension that they discovered. And the two surfaces on the sides are ordinary space-time. So the picture that arises here is that the world we realize is confined to one of those surfaces. So our four dimensions of space and time are one of the surfaces of this slab. So we have a four-dimensional surface. We have a one dimension across it. That makes 5. But I just said there are 11, so there's 6 more dimensions. So the other 6 dimensions are curled up so tiny that for almost all practical purposes, we can ignore them. So a very good approximation to start with is that there's just 5 dimensions where you have a slab with 2 4-dimensional faces, and we are confined to live on this one of those 2 faces. So that's the picture. The mathematics clearly points to this. There's no doubt about that. Whether this is the right theory of nature, I don't know. But I would say that among all the developments in string theory so far, it's the most promising possibility. It's a fantastic subject because there's actually experimental observations going on. So it's not just some crazy theoretical idea like I've been talking about. It's something we know is really out there. And people looking at gravitational waves and other things are learning enormous amounts about them. Black holes are one of the features that of Einstein's general theory of relativity that Einstein didn't find those solutions himself. Another person named Schwarz was the first, a couple of years after Einstein's work, to show that the equations had that kind of a solution. For many years, it was unclear to people whether they were just some mathematical artifact or whether they were things that really exist. And now we know, of course, that they really exist. And some of them in the early universe and far away are absolutely enormous. There are ones. There's one that they even took a photo of, which whose mass is 6 billion times the mass of the sun. And the black holes have many incredible features. One feature is that their size, let's say their diameter, is proportional to their mass, which is very weird. Because if you just think of an ordinary object like the sun, the mass would be proportional to the cube of its size, because its volume. So in the case of black holes, it goes linearly with the size rather than cubic, as you would ordinarily expect from an ordinary object. And that's again a feature of these mathematical solutions of Einstein equations. And the mathematical properties of black holes have been tested. Considerable accuracy, and Einstein's theory works. There's no chink in its armor so far. It works. At some point, there are issues it does not address, that where quantum theory comes in, and that's where string theory should be helpful. One of the important features of string theory discovered by Hawking quite a few years ago is that they have thermodynamic properties, such as entropy. And he wrote down a formula for the entropy of black holes, which basically implies that the number of quantum states of a black hole is proportional to the area of its surface. The surface being what people call the event horizon. In fact, Hawking's formula is even more accurate than that. It's 1/4 of the area. And in special examples, people using string theory techniques were able to count the quantum states of a black hole and to verify Hawking's formula for these examples. So that was also done in the mid-90s by 2 string theorists, Strominger and Rothman, who are important. They're both professors at Harvard now, and both continue to make important contributions to the subjects. So everything you said in your question is correct. As I mentioned, supersymmetry is one of the features that's incorporated in our string theory models. There is as yet 0 experimental evidence for supersymmetry. And what's been clear from the beginning is that this symmetry is not going to is what we call a broken symmetry. there's a precise mathematical meaning to what it means to be a broken symmetry. And it doesn't just mean that it's approximate, it's a deeper meaning than that. The meaning is that it's an exact symmetry of the fundamental equations, but the solutions to those equations that describe nature do not preserve the symmetry. So it's that's a little bit subtle. And so that's the kind of symmetry that supersymmetry has to be. It's an essential feature of any potentially realistic string theory. So supersymmetry must exist if you believe in what I'm talking about. And but at least open the question of what is the energy scale at which the symmetry is broken. And prior to the LHC experiments taking place, various theorists gave arguments that the symmetry breaking scale for supersymmetry should be approximately at the energy where this accelerator would be operating. And if that was correct, that meant that they had a good chance of discovering new particles that would be the supersymmetry partners of known elementary particles. And such a discovery would be revolutionary because it would enable us to construct a whole new standard model incorporating whatever was learned from such experiments. However, as I said, there were several arguments for why that might be the right energy scale. And as Feynman used to always say, when you have several arguments for something, it means that you don't have just one that's very good. And all of these arguments are kind of hand-waving, and there was uncertainty. There's no question that string theory requires supersymmetry at some scale. But my current opinion, which has sort of changed over the years, is that the scale of supersymmetry breaking is going to be much further, much higher than is experimentally accessible. I wish it were otherwise. I was hoping that the accelerators would find supersymmetry, not because I had some personal stake in it, but rather because it would be so informative that by studying its properties, we would learn much more about the fundamentals of physical law. But nature was not kind to us in that respect. And now at this point, I'm pessimistic that it'll show up at the LHC. They are improving the accelerator. They will search a little further than they have so far. So it's not out of the question that it'll still be found. But I think at this point, most people would agree that it looks quite unlikely that they will find it. Certainly, in our attempts to relate string theory to the real world, there's no difficulty to put string theory at a much higher, to put supersymmetry breaking at a much higher energy scale than the scale at which the LHC operates. There was this important paper written by Juan Maldacena in 1997, which initiated it. There's a mathematical fact that I knew and failed to take advantage of, even though I've always advocated taking coincidences seriously. And that is the symmetry of a conformally invariant theory is the same symmetry as the symmetry of a negatively curved spacetime, what's called an anti-de Sitter spacetime. And in the real world, what's called the dark energies suggests that our universe actually is positively curved, not negatively curved. It's what we correspond to what's called de Sitter space rather than anti-de Sitter space. Negatively curved is called anti-de Sitter space. Positively curved is called de Sitter. The way to visualize these things, a sphere has positive curvature and a saddle has negative curvature. So in the case of negative curvature, there is this beautiful correspondence between quantum field theories that have conformal symmetry and string theory solutions that have anti-de Sitter symmetry. And that's been a very active subject ever since its initiation more than 25 years ago. In fact, Maldaceno's paper, I think, is the most highly cited paper in theoretical physics ever. Well, people didn't count these things until relatively recently, but anyway, it's very highly cited. So that's a beautiful subject, and people learn a lot from thinking about it, but it's not realistic. It's not realistic. So it's a wonderful subject. I've looked into it a little bit myself. If you're trying to describe the real world, that's not the way to go. So in this Maldacena correspondence between anti-de Sitter spacetimes and conformal field theories, what you are doing is relating a conformal field theory, say in n dimensions, to an anti-de Sitter space in n+1 dimensions. So you're encoding the same physical information in two different formulations, one of which has one more dimension than the other. And that's reminiscent of holography, where you take a picture of the three-dimensional world and you put it on a two-dimensional surface, and yet you can see it as three-dimensional because the information is encoded so cleverly. And for this reason, people refer to this ADS-CFT correspondence as a holographic correspondence. It projects down one dimension. But as I was saying earlier, as far as I can tell, while it's a beautiful subject and it's good mathematics, I don't think it's directly related to anything that's realistic. It's possible that artificial intelligence will be helpful for physicists trying to understand things. It's never going to replace them, in my view, but I think it could turn out to be useful too. There are two answers which are inconsistent with one another. The first question is to follow your passion and do what you truly want to do and believe in. That's answer number one. And the second answer is to do what will make a pleasant, comfortable, happy life for you. And the ideal situation is when there's an overlap between those two categories. And I feel fortunate that I've, in my career, been able to fall into that overlap. But it's a very individual matter how to reconcile those two things. Also, I think it's useful to try to be objective in assessing what you're able to do and what you're not able to do. Different people have different strengths, and so you need to figure out what it is you're good at. Usually what you're good at is what you enjoy doing, I think. And so there's a consistency there.